Good afternoon, everyone, and thank you for attending our Successful Flex and Rigid Flex Designs for Streamlining Production webinar. My name is Kendall Paradise, and I'm the president here at EPIC. Before we get started, I just want to let you all know that you'll be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel located in the webinar control panel, and we will try to get to them at the end of the presentation. If we don't have time to go through all of your questions, we will be sure to reply back to you via email. Also, we will be recording this webinar and we'll be posting both the recording and the slides on our website and YouTube channels. If you visit epictech.com/webinar, you can access our entire archive of webinars and view upcoming webinars. Our presenter today is Paul Tomei, our Flex and Rigid Flex product manager. Paul holds a mechanical engineering degree from Seneca College. As product manager, he oversees our entire Flex and Rigid Flex product line. Though Paul's main responsibility is customer technical support, he is involved in each project from beginning conceptual stages to delivery. He works directly with our customers on their specific design requirements and makes sure that each product is designed correctly, troubleshooting any issues that may arise. Now I'm going to turn it over to Paul.
Thank you, Kendall. And again, thank you everyone for joining us today. There we go. So our webinar today is based on streamlining flex designs for production purposes. And the definition of streamline that we're using today is a design that's arranged to offer the least resistance, it's reduced to its essentials, and it's effectively organized or simplified. Rigid flex and flex, as compared to rigid boards, have a significant increase in the amount of materials used and in the production process steps involved. You also get many additional items in flex and rigid flex that you don't traditionally find in rigid PCBs. And all of these additional items will add materials and add process steps. And in more complicated designs will interact with one another and potentially create additional design or technical challenges. Streamlining, we found that streamlining a flex or rigid flex design has a much greater impact on the delivery and the cost of the project than what you would find in a traditional rigid board. So as part of the introduction, I just wanted to cover very quickly some of the basic differences between a two-layer rigid and a two-layer flex so that we can have an understanding as to where these added elements come from. In a rigid flex, or in a two-layer rigid board, I should say, you'll have a rigid core with the copper, you'll have solder mask and a silk screen. And I know I might be generalizing a little bit, but this is just to give us an overview. The production processes are typically drilling, plating, creating the circuit imaging, applying the solder mask, applying the required surface finish, the silk screen for the nomenclature, electrical test, you do your outline routing, and you package it and ship it. So on average, you're going to have 3 different types of materials and approximately 8 process steps, or 8 significant process steps, I should say. Now, comparing that to a two-layer flex, you're going to have your flex core with the copper, you're going to have cover lay as opposed to solder mask, although in some designs you may actually have both. The silk screen, very common to have stiffeners, be them either made out of F44 and or polyimide. In some cases, you'll have both on a given design. And you may also have a PSA, which is an acronym for a double-sided tape, which you'll use to adhere the flex within your assembly or enclosure. For the processes, we now have the drilling, the plating of the vias and the PTH holes, circuit imaging. Now for the cover lay also requires a manufacturing steps in that it needs to be routed and drilled in order to create the openings required for your components. You now have another significant step and you have the cover lay lamination. You have solder mask application if required, surface finish, which is common. Then you get into the stiffeners, where you'll have additional drilling and routing process steps required to shape the stiffeners to the required configuration. Stiffeners now have to be laminated. The same applies if you have PSAs, where you may have you'll have drilling and routing requirements to profile the PSA. You then need to manually apply the PSA to the part. Then you finish it off with the same silkscreen, electrical test, and outline profiling. But as a comparison, you can see the materials now increase on average from 3 of a rigid PCB to 6 for a flex circuit, and the processes have jumped up from 8 up to 17. Moving on to a 4-layer rigid versus a 4-layer rigid flex. I'm not going to go through all of the details of the process steps, but the significant element here is that the materials in a rigid PCB increase from 4 different types of materials and 10 process steps up to 7 different types of materials and 17 process steps. So every time you have more materials, you have additional costs. Every time you have more process steps, you have additional costs and additional time taken or required to manufacture the flex or the rigid flex. So in our agenda today, we're going to cover some design for manufacturability reviews, design and construction methodologies, material selection criteria. We're going to talk about the manufacturing data sets. We're going to get into a few specifics and how they impact the flex or rigid flex, that being impedance requirements, if you have vias or plated through holes in flexible areas of your design in a rigid flex. And we're also going to touch upon the additional features that you can encounter in a flex or rigid flex, those being stiffeners, PSAs, shield layers, and epoxy strain reliefs. So first item is design for manufacturability reviews. This is something that we do and we recommend to all of our customers to be done very early on in the design development process. In some cases, we perform this to varying degrees right at the initial concept stage when working with a customer in helping them to validate the design direction that they're going with for this specific application. As the design develops, in many cases while we're working with our customers, we'll repeat the DFM review to ensure that we're on the correct track, that we're not going to encounter any significant technical issues as we move forward, that we're not incurring any significant cost additions, or at least if the customer is, they're doing so forewarned and with full knowledge. And ultimately, by following this process, without a doubt, it definitely prevents the customer from running into roadblocks and delays as the design develops and they get closer to finalizing it. A key element in the DFM process is applying the guidelines that IPC has established in their 2223C sectional design standard for flex and rigid flex printed circuit boards. This standard covers quite a lot of ground. It's very detailed, deals with a lot of the capabilities that are present in the industry, deals with a lot of items that relates directly to the manufacturability and also to the reliability of the finished part. This is our Bible. This is the primary document that we apply as we're going through the DFM reviews with our customers. Now, having said that, 2223C is all-encompassing. There is a lot of information in there. And we find the area where we're of specific benefit to the customer is reviewing their design, identifying the specific elements within 2223C that pertain, and basically brushing aside all the rest that is irrelevant and allowing our customer to focus on what is important to their application. So moving on to design and construction items. Rigid flex construction, there are a wide variety of combinations that could be performed, or configurations that can be applied, I should say. From the top image, That is the preferred configuration. The flex layers are located in the center of the material stack up. Technically, it has advantages in that it'll minimize any warp and twist that might occur, specifically once you panelize these parts into a larger array configurations. It simplifies the manufacturing process, and it, in the majority of cases, allows for the design to have improved flexibility. The bottom image shows an alternative construction where the flex layers have been pushed down to the bottom of the stack. They exist as layers 3 and 4 in this 4-layer example. It's manufacturable. There may be some situations where it's a necessity, but we always review this requirement with our customers to see if the preferred balance build construction can be applied, which will, as I said, optimize the process. Another key element that's encountered on the vast majority of designs is whether or not a rigid flex versus a flex with stiffener design can be applied to the solution. Many of our customers will come to us believing that they need a rigid flex to meet their requirements, but once we've had an opportunity to review, we'll put on the table for discussion whether a flex with stiffener configuration is going to meet their end requirements. It's a much more cost-effective solution as compared to a rigid flex due to primarily the reduced material requirements and process steps, but there are application limitations. So understanding the requirements is a key part of moving forward in this area. Rigid flex, definitely a much more capable technology, but with that, it does bring increased costs in materials and process steps. Another key element is the size and shape of the part. And this element here has significant impacts on the cost of the design. It impacts the material requirements, the material utilization that we can achieve from our production panel. That in turn will dictate the number of production panels required to meet the customer's order quantity. And in some cases, if it results in extremely large panel, can start to negatively impact the yield rates of the parts as you start to accumulate material and manufacturing tolerances on these larger types of parts. From the example that we have on the screen here, you can see there's a lot of black unused space. Now that's all materials, that's at a cost. We strongly suggest to all of our customers that they get input from ourselves or their chosen manufacturers to review the assembly array, review the part configuration, size, and the assembly configuration to try and come up with an optimum solution. On the screen right now is an example of a design that we worked with a customer. On the right, or sorry, I should say on the left, in the initial draft is what the customer came back, initially presented to us as their requirements. As you can probably see, trying to panelize this into a production panel for manufacturing purposes would be similar to the previous example we had on the screen, where you would end up with a lot of unused space in the production panel, which would significantly increase the cost. So we had a discussion with the customer as to how they were going to apply this part. And the end result was the two bends, the two 90-degree bends, were actually not necessary, that they could allow the flex to bend of its own fruition in the final assembly. The end result was the revised design you see on the right, where we came out with a nice straight rectangular part shape, allows it to be panelized into the production array extremely efficiently. And I think for this specific example, ended up reducing the cost of the part by about 40%. So it was a significant change. So moving on into material selection. The industry runs on, the vast majority of the industry runs on what we're identifying here as the common industry materials. So copper would be 1/2 ounce or 1 ounce in either a rolled annealed or an electrodeposited format. The flex cores will vary from 1 thou to 3 thou in thickness, and that can be either adhesiveless or adhesive-based flex cores. And the coverlays will vary in thickness from 1/2 mil to 1 mil in thickness of the polyimide, with then either 1/2 mil or up to 2 mils worth of adhesive. The adhesive thickness needs to vary according to the copper thickness that you're working with to ensure that you encapsulate and laminate the coverlay on correctly. Another element in material selection that's important to note is that there's a significant difference in the format of the materials comparing offshore production versus domestic production. Offshore runs on a 250 millimeter wide roll format. 500 millimeter wide roll formats are also available, and the rolls can be either 50 meters or 100 meters long. Domestically, almost without exception, runs on panels, and they'll start off at 1824, and then they can cut them down from there. They can go down to a 9 by 12 or a 12 by 16. So the part size and how it fits into the available material formats and how the production array, the assembly array is configured, you definitely need to take into account the available material formats to come up with an optimized solution. Moving on, data sets. And this is an area that we work with our customers with significantly. The data sets that we see, especially when we start off with working with a customer at a conceptual stage, the data set essentially doesn't exist at that point in time. So we're going to work with our customers to optimize the data set and ensure that it contains all the relevant manufacturing and QC standards, all the relevant material specifications, and we recommend to our customer that the materials be defined by the IPC material specifications so that you don't get locked into a specific brand or part number of material that may cause availability issues. Identifying critical dimensions, ensuring that the correct and detailed material stack-up is part of the data set, ensuring that the data set is complete for the Gerber files. Now, our customers typically don't have any issues generating the Gerber files for the circuit layers, but where they can run into some issues is for how do they present the information for required stiffeners, for PSA layers, shield layers, and epoxy strain reliefs, all elements that they don't typically encounter in rigid board designs. And that's a significant area where we work with our customers to identify those requirements and ensure that they are properly documented. Moving forward into something a little bit more specific, and that's impedance requirements on high-speed designs. We find a lot of our customers will come to us with designs that require impedance-controlled circuitry, but they'll do so from their knowledge base, that being primarily rigid board designs. We'll see that and we'll identify a number of areas of opportunity to discuss with them to drive cost out and to streamline the design. First is the construction of the impedance. Does the customer require the impedance to be configured as a strip line 3-layer construction where you'll have a reference plane, a signal layer, and then a reference plane? Or is a surface microstrip, a 2-layer configuration of signal layer and reference plane, going to meet their requirements? In the flex side, in the flex industry, there is a preference towards the surface microstrip, primarily because it allows for a much thinner and much more flexible flex construction, which is going to give you a higher degree of bend capability and a higher degree of mechanical bend reliability. So common configurations for high-speed signals in flex is the dielectrics are going to range from 2 to 3 mils. The line widths are going to vary from 3 to 4 mils, and the line spacings will vary from 5 to 7 mils. These parameters cover a wide range, everything from 50 ohm single-ended to 90 ohm differential pairs, 100 ohm differential pairs, and even up as high as 120 ohm differential pairs. And as I stated at the beginning of this section, many of the designs that we see are not initially optimized for flex applications. They're using PCB design rules, applying much thicker cores than what are ultimately necessary. Those in turn limit the flexibility and mechanical reliability of design. And we have seen many designs where they're just not going to meet the mechanical bend requirements that the customer has for that specific design. So moving on to a little bit of a unique element that you see in flex and rigid flex that you don't see in rigid boards is via holes and plated through holes that exist in the flex areas. Some of the applications where you will require this are if you have to have, due to mechanical reasons or space limitations, components down on the flex layer as opposed to constraining them or constricting them to the rigid areas only, as you can see in the example on this page. And another application is for shielded layers, stitching the shields together down the length of the flex for as an effective shield as possible. Now, vias and plate-through holes in the flexible areas are definitely significant cost adders and process steps adders. They require additional drilling and plating processes. Excuse me. So instead of having one drilling and plating process, you now are going to have at minimum 2 of each. The plating process is a little bit more involved than a traditional rigid board plating in that it's what's known in the industry as a selective pad plate process. The plating is constricted to the hole location only so that you don't end up with additional copper plated on the surface of the circuitry, which would then be detrimental to the flexibility of the design. And depending upon the surface finish, you may get into some masking issues where you have to mask off the work that you've done or the features on the flex circuit, which again can add some significant process steps and costs and complexity to the design. So to summarize, it's a design element that's available, but we strongly suggest to our customers that it's applied when it's required, and you make an effort to avoid it if possible. So moving on to some of the additional features that you encounter in flex and rigid flex. So the most common one are stiffeners. The application of a stiffener is to support a component area so that you don't have the opportunity to bend the flex adjacent to the components and potentially compromise solder joints. And the other common requirement is to increase the thickness of the part to meet a specific zip connector thickness requirement. And in the example we have on the screen here, on the underside, you can see the FR4 stiffeners supporting the component areas, the small BGA components, and at the ends of the flex extensions, you can see the darker polyimide stiffener applied to achieve the zip connector specifications. Each stiffener thickness, each stiffener material is going to add process steps and costs, and can, in some cases, result in many additional lamination cycles and profiling and drilling processes to create the individual stiffeners. As an example, if you have 4 different stiffeners of different thicknesses and different materials, you're going to be looking at 4 different lamination cycles, which is a significant process step. So while the cost of the stiffeners themselves are minimal, the delivery can be significantly impacted. And again, we work with our customers to ensure that stiffeners are applied where they're required. Another common element are PSAs, or as I mentioned before, double-sided tapes. Application is to adhere the flex circuit within the enclosure. And in some designs where the flex circuit is required to bend hard back upon itself and achieve a zero bend radius, you typically apply a PSA in that area to prevent the flex from being reopened and potentially damaged. Again, we're looking at additional materials and process steps and cost for each of the different types of PSAs. We've got multiple profiling, drilling, and application processes now required. And in a similar fashion to stiffeners, while the cost of a PSA is minimal in the overall cost of the design, it can have a significant impact on the delivery of the part. So moving on to shield layers. And shield layers are a design element that are becoming much more utilized and popular in the industry today. Primarily used for EMI and RF shielding, they replace the additional copper layers that were a common solution in the past. They also replace silver ink layers, which were the initial alternative to copper layers that were used for many, many years. The advantage of shielding layers are they provide substantially improved flexibility at a significantly lower cost over additional copper layers. So this is an area of some of the designs that we work with where you can really streamline the manufacturing process by applying a shield layer, a specific shield layer, as opposed to the alternatives of copper layers or the old-fashioned silver ink. The shield layers are laminated on top of the cover lay, so there's no additional drilling processes, no additional plating processes. The shield material has a electrically conductive adhesive, which through selective openings in the cover lay that expose ground lines in the circuitry, the shields laminate on and electrically interconnect to the ground through the conductive adhesive. By far, it's the preferred option for shielding designs that are not impedance controlled. This is an area also where our customer base tend to need our support in applying the shield layer correctly. Many CAD systems don't have the configurations available to effectively apply a shield layer. There are limitations as to where it can't be applied. So that's a significant element of optimizing the design, and also one where our customer base requires support. Next item is that we're going to cover our epoxy strain reliefs, or an acronym used or a name used in the industry is EcoBond, which is one of the manufacturers of the material. So the epoxy strain relief acts as a mechanical strain relief at the rigid to flex transition, and it prevents the flex circuit from being bent at a sharp angle and potentially creating a crease at the rigid section if it was to be inadvertently bent in close proximity to the rigid. By allowing the flex to bend hard and get creased at the rigid to flex transition, you could potentially run into circuit breakage. Again, it's an inexpensive option, but it can significantly impact the delivery of the parts. The material is applied in a mechanical method, is manually applied, primarily due to the fact that it's a two-part epoxy system, which doesn't play well with automated application systems. Those systems tend to work well with one part, not where you have to have materials mixed and have a finite working time frame. You apply them at the bead to one side of the design. Before you can apply it to the other side, you need to go through a baking process, which can vary. It can be in the range of 2 to 3 hours to cure the material. You then come back, flip the part over, apply it to the second side, and again perform a baking operation. We see lots of designs where a customer is stipulating the need for an epoxy strain relief. From our review of the design, we question as to whether or not it is a necessity. So at that time, we'll have the appropriate discussions with our customer. In many cases, it's not a requirement. It's just a default parameter that they happen to include in the design. But is it a necessity for this specific one? No, it's not. In other scenarios, it may be a requirement at one of the rigid to flex transitions, but not all of them. So that's part of what we'll cover with the customer to streamline the design as much as possible. Again, falls under the category of use where and when required. So in summary, to streamline or optimize a flex design requires that process to be started almost right at the conceptual stage. We reviewed the design, or the design needs to be reviewed multiple times over as it's being developed and moving towards being finalized. We strongly recommend to all of our customers that they get input from their supplier. Design elements can and will interact. So looking at the design elements as individual items, not necessarily an issue, but combining them can create potential additional manufacturing complexities and costs. And getting input for material selection and material utilization feedback. Again, going back to the part size, shape, the assembly array configuration, and production panel material utilization. All of the design elements need to be evaluated at the prototype stage. Once the design is finalized and we've moved on into the prototype stage, we work with our customers to review, again, all of the design elements and validate that they are indeed necessities for this specific design. And if not, then go back and adjust the design with the ultimate goal of optimizing it or streamlining it as much as possible from a production point of view.
Thank you, Paul. Just as a reminder, in addition to flex and rigid flex PCBs, we offer a wide variety of products, including battery packs, cable assemblies, rigid PCBs, RF products, user interfaces, fans and motors, and our latest product addition, flexible heaters. You can learn more about all of these products on epictech.com. Now we will go over the questions that came in. Remember, if time doesn't permit us to answer your question, we'll reach out to you by email.
Thank you, Kendall. So from the questions that we received, we picked 4 of them that we're going to cover today. And as Kendall mentioned, all of your other questions will be reviewed and answered, and we'll get back to you through emails. So the first question we got was, are there limitations as to where shield layers can be applied? And the answer to that is definitely yes. Shield layers have a slip property to the external coating of the shield layer. So as such, you can't laminate anything on top of a shield layer. So shield layers cannot extend underneath stiffeners, for example. Because shield layers are applied on top of the cover lay, you need to account for material and manufacturing tolerances. So openings in the shield layer surrounding surface mount components, as an example, need to be sized accordingly to take into account all of those all of the involved material and manufacturing tolerances. This is something that we work with our customers. We review the design, identify the shielding requirements, and from that, we'll then put together an initial, in many cases, we'll then put together an initial Gerber file of the shield layer, submit that back to our customer for their review. We'll have further discussion, optimize it as required, and move forward from there. Second question we received regards reliability of the various constructions. And the question is a flex with stiffener construction as reliable as a rigid flex construction? The simple answer to that is, in the majority of cases, yes, it is. If it meets the balance of the design requirements, it won't bring a reliability concern along with it. The only small percentage situation is when you have connector systems that could potentially be plugged and disassembled many times over. If those connector systems don't have any other additional mechanical attachment methods, then a rigid flex may be the preferred scenario. But again, the percentage of that is relatively small. Third question that we're going to cover refers to material lead time if a design requires a non-standard stock material that we covered earlier. Lead times on materials will vary depending upon the volume and the manufacturing location. I think it's fair to add at least 2 to 4 weeks for non-standard stock materials, and that's provided that it is a standard manufactured configuration. If it is now a unique custom, the lead time on materials can easily grow into the 4 to 8 week range. And the last question we're going to cover is, and we run into this or encounter this one on almost on a daily basis, is design support available if our CAD system does not support the added features required, such as stiffeners and PSAs? And that's a big part of the support mechanism that we offer to our customer. We understand that CAD systems are not may not be configured to their fullest for flex and rigid flex requirements. So supporting our customers with that part of it is a big part of what we do. We'll create Gerber files, submit that back to the customer so that they can visually see exactly what's required, giving them an opportunity to either move forward as is at a Gerber stage level or go back into their CAD system and apply implement the requirement. So again, we appreciate your attendance today. Thank you very much. Any questions you've submitted, we will be reviewing and answering back to you directly. And we appreciate your time. Thank you very much.